Hello and welcome. I'm live to another calculus stream here. Welcome, welcome, welcome. Oh, hello, hello. We're doing more volume stuff today. This time we're doing revolutions, which is actually an easier volume thing. So, that's pretty cool. Too shabby. Hello, Michael, Kelly, and Drew. Welcome. I'm starting off with posting this question because I'd like people to try this out. People struggled a bit with going over the y-axis, so looking at more examples of this style is probably worthwhile. Fun rhyming. Yeah, that's why this. Hello, Keith. Hello, Caitlin. Do seniors have to continue after our last day for this class? No. Hopefully this will have less problems than last time. Did the last one take a long time, Michael? Is that what you're implying? Hey, Andrew. Welcome. Hello, Chelsea. Because it is fewer problems than last time. I think the assignment's 7 questions instead of 8. So less. Can you do 5? Couldn't get it. I believe 5 is one of the ones I'm going to be going over shortly. Because I picked out the 3 that were the most missed, and I looked in all the classes, and there was like consistency in that, so that's where I'm going to be taking a peek. Yeah, Nick, that second Y one is 5 then. So, yes, I will be doing that one. I do recognize. Would be good there. Oh, people in chat causing problems. Yeah, that would be cool. It had been a while since they had visited, so I think it's just random bad luck on that front. Oh well. All right. I want people to have a chance to take a peek at this problem and try it out before I go over it, so I was going to give it another couple minutes. Drew is done, but Drew was one of the first ones here, so not a surprise there. Surprises. Nick, I'm still holding out hope that it's not going to be invaded again. So we'll see how that goes. If it doesn't go well, I will address it before the next stream. I will fix the issue. But for now, I'm hoping the issue will not resurface. I could do all those things. It just makes it a little less accessible for people in general, and I'd prefer not to make things less accessible if I can help it. So, trying to help it. Are there going to be YouTubers chat invasion again? So far, no, Daikun. If there are, it's something I'm going to have to address. Hopefully there will not be. they've showed up all of twice in, like, in a disruptive way. They've showed up all of twice in a ton of times that I've done this, so I am not overly pessimistic on this front. I agree. Folks, we're kind of beating this horse to death at the moment. It needs a chance to recover here. Tycoon, I do realize it happened both this year. I am not stupid. You guys, please leave this alone, alright? Don't be as annoying as the people who invaded. When is the last day for seniors? Do any of the seniors know? I've been having a heck of a time actually finding it. The stuff from the district is very complicated. I think it's next week sometime? Maybe it's this week? I was thinking about making this the last assignment that I make seniors do, but I don't know for sure what the right play is. Yeah, graduation's on the 12th. It kind of makes sense that today is the last day. It's interesting we haven't even gotten the gradebook is open notice for seniors yet, which is curious. Yeah, the good news is for textbooks, we don't use the textbook anymore, so no problemo there. So, underclassmen, you guys have more assignments that will be due. And by underclassmen, I mean not seniors in this case. Whereas the seniors, this is probably the last assignment I make them do. And this is a pretty decent end point. Liberty e-news? Huh. Yeah, I can see it on my calendar that the textbook drop-off day, but they have been really unclear, and we have not had our gradebook open yet for you guys, for seniors, so that means grades are not a week away from being done yet. Alrighty, I'm going to start by going over this question. Gosh darn it. I do that right as my stupid McAfee thing shows up. Alright, whatever, dude. So the reason I picked this is the most missed questions on the homework were definitely all the ones that related to the y-axis. So for the y-axis, you actually need to solve for x in each of these equations. So x equals y squared. And, well, x equals y is the equation solved for x. Because we need to define everything in our problem in terms of y's. Now, if I look at the picture here, square root looks like this, y equals x looks like this. Now, coming from the y-axis here, which is what we're doing, I should not draw that line, that's not a helpful line. It's more like this is the helpful line, because this is the base of our shape. We're doing little semicircles up in space like that. You need more of these to kind of get a picture of what this thing looks like. It looks something like that. Some sort of like half banana sort of thing here. This distance here is y minus y squared. For any point on here, it's the farther out one, which is the line, y, minus the closer in one, which is the curve, y squared. And by closer in, I mean closer to the y-axis, because that's what we're perpendicular to. Okay, so y minus y squared is my diameter, which makes my radius y minus y squared over 2. Now, the equation we're trying to solve is 1/2 pi r squared, because it's a semicircle. And I just plug in r. So I get 1/2 integral. I guess I can pull the pi out too. And r squared, y minus y squared over 2 squared dy. I should get my bounds. So where do root x and x meet? Well, it's at 1, 1, because Square root of 1 is 1. They match at that point. So we're going from 0, 0 to 1, 1. So it didn't matter whether we were using x or y's. Our bounds are 0 and 1. Now I have to square the inside, the integrand, in order to actually solve this, because I can't deal with the y minus y squared thing. So I just FOIL y minus y squared minus 2y cubed plus y to the 4th over 4. And at this step, I can actually just pull this over 4 out and make it an 8 out here. So I'm going to do that, a 1/8 pi times the integral of all that junk. And now it's like a really easy integral. It's just power rule. So I get 1/8 pi evaluated at 0 and 1 of y cubed over 3 minus 2y to the 4th over 4 plus y to the 5th over 5. And you just plug in 1. So the answer is whatever 1/8 pi times what 1/3 minus 1/2 plus 1/5 is. And I believe we had 1/3 minus 1/2 plus 1/5 in our notes. That's 1/30th. So this is pi over 240. That's not very big. That's a really, really tiny volume. Why is it 1/8? So Liam, at that step, I realize I may have lost people there. At that step, I actually had this 1/2 pi times y squared minus 2y cubed plus y to the 4th over 4, because I had squared the 2 on the bottom when I expanded y minus y squared over 2. And all I did was say, hey, this 4 on the bottom, I'm just going to take it to the outside here and make it a 1/8 on the outside, because that's the same thing. Why is it y minus y squared? It's y minus y squared because, okay, first of all, it doesn't actually matter because we're squaring it, whether or not it's y squared minus y or y minus y squared. They give us exactly the same thing. So the nice part about when you square things is it doesn't matter which one you get on top or on the bottom. When you square it, it's always positive. So all that really matters is that you're squaring the distance between the curves, which is either y minus y squared or y squared minus y. It's the outside curve minus the inside curve in terms of that distance. Yeah, you look at the graph on its side. So yeah, if you turn your head 90 degrees to the right and look at the graph, you look for the one that's on top when you do that. Or if you turn your screen 90 degrees to the left. So that, yeah, x is in the up direction for positive, then you can figure out which one's on top and which one's on the bottom. But the moral of the story is, because we're squaring it, it doesn't matter. You could have used either of these, you get the exact same inside. Can you explain why it's y minus y squared divided by 2? Absolutely. So y minus y squared is the distance between the curves. But we have so if I redraw this, because I drew way too much down there, these are our two curves, and this distance is the diameter because we put a semicircle up into 3D at any given point along here. And I need the radius in order to find the area, because pi r squared is my area equation for a circle, so it's half of the distance between the curves, half of the diameter piece there. Did I answer people's questions adequately? I can tell it's worth it to go over these more because people did really well on the X ones on average, and the Y ones were brutals. So I'm going to go over more of these because the next thing I'm going to do is pop over to the questions I grabbed from the homework. And almost all of them were Y questions, but this one wasn't. The first question on the homework was the most missed. I wonder if it's just because it was the first question and people like got better at this as they went along. Maybe. Or maybe something else. Okay, so in this one, we have the base of a solid is... Uh-oh. Okay, no, I didn't break it. Good. The base of the solid is a region bounded by the x-axis and the curve of the square root of 1 minus x squared. Okay, so what does the square root of 1 minus x squared look like? Well, if I plug in 0, I get 1. Cool. And if I plug in 1, I get 0. Cool. Also, if you square both sides, you get y squared equals 1 minus x squared, which if you add x squared over, you get x squared plus y squared equals 1. So this is a circle, but it's because it's just the positive part of a circle, it's just this part up here. So that's all we got here. So you can try plugging in values and seeing what happens. If you plug -1 in, you also get 0. Or you could solve this and figure out that the parent graph is a circle, or graph it in Desmos or something like that. But the moral of the story is this is our shape, our base, and we're putting squares up into 3D. That square looks like really crap. And I deleted my axis. Good job. All right, so we're putting squares up into 3D. So this is the base of my square here. That is going up into 3D, and I'm afraid to draw it because it's going to make the picture look even more convoluted. Something like this, up in 3D. Okay, so that distance is mercifully only square root of 1 minus x squared. So when I go to make my equation, it's integral of side squared. Side is just the square root of 1 minus x squared. It's the x because the equation's in terms of x and we're perpendicular to the x-axis. We're going from -1 to 1. And I can already see that these people went from 0 to 1 because that's how they got half the correct answer. So that was definitely the most common mistake on this. If I now integrate from -1 to 1 of just 1 minus x squared dx, which is what you get when you square a square root, all you get is evaluated at -1 and 1 of x minus x cubed over 3. And then you just plug in the bounds. So it sounds like, look, you get 2/3 for this one. But then you also subtract -1 plugged in, and look at this. We get 2/3 minus a -2/3, which is 4/3, which is the answer. So we can see what people did wrong there. It was just only doing half the picture and doing the integral from 0 to 1. Negative is messing you up. Oh, feels bad. The other way to avoid doing any negatives is to realize that in this question, if you cut this in half right here, it's the same on either side. And so you could actually just do the integral from 0 to 1 multiplied by 2 of 1 minus x squared dx and avoid having to do really any negatives. So this is perhaps the easier way to do this, if you realize, and you save yourself some hassle. But totally optional to do that. All right, moving on to our second one. This is one of the y ones. So we have cross sections perpendicular to the y-axis, which have a rectangle whose height is 4 times its width. So we know our equation is like 4x times x, or like 4x squared, or 4 side squared is maybe a better way of putting it. Since if I call the base s, the height is 4s, so this is like height times base. And so we get 4s squared for the equation of our rectangle, just generically. We're perpendicular to the y-axis, so I need to solve for x in my equations, get my equations in terms of y. I only have one equation, y equals cosine of x. Easy to solve for that. X equals the inverse cosine of y. Maybe it helps to know what the picture looks like. It's a really easy picture to do. That's cosine from 0 to pi over 2. That's the thing we're... this is the base of our shape. And what we're doing here is we're putting cross-sections of like tall rectangles up here. So this is just a very tall piece up in space here in our shape. So I now know everything. This x distance is my side length. So I'm integrating 4 times the inverse cosine of y squared dy. I'm integrating in the y direction, so instead of going from 0 to pi over 2, I'm going from 0 to 1, because I'm integrating across y. And then you just chuck this in a calculator. I mean, this is just that you have no tools to integrate this. This is just straight Desmos land. And doink. Are people cool with that, or do they want to see me dump this into Desmos? Can we get a break? I can hang out for a sec. Been going a little heavy here. No inverse trig. No inverse trig. No, like, integrating inverse trig is not something we did. We integrated to inverse trig, but we don't do inverse trig. All right. Yes, we are doing new stuff today. Alrighty. Moving forward. I didn't notice we had a new question there. Cool. So now we have the base of a solid is the region in the first quadrant bounded by... Why do we go from 0 to 1 instead of 0? Okay, so let me go back before I finish explaining this. The reason why we go from 0 to 1 is because if I take out cosine of y here from 0 to pi over 2, 0 to pi over 2 is my x bounds. My y bounds, it starts at 1 and then goes down at pi over 2 and gets a 0. Yeah, I see. Well, our next stream will be private. All right. So, if this question had been perpendicular to the x-axis, I would have had the integral from 0 to pi over 2, and I would have used cosine of x as my distance, and it would have been 4 times cosine of x squared dx like this. And this is actually something we would have probably had the tools to integrate, actually, 4 cosine squared of x. I'm not sure that I know how to do this. Dun 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 dun. All right. Hopefully that answered your question, Drew. Okay, I want to move on and do some y-axis rectangles. Here, very similar. Perpendicular to the y-axis, rectangle whose height is 5 times its width, which means 5 sides squared is my equation. I need to solve this for x, so it's in terms of y, in order to plug it in correctly, because we are perpendicular to the y-axis. I can graph this real quick. If I plug in 0, I get that it starts at 2. It's going down with a slope of 2/3, which means it goes down 2 over 3, so it means it goes to 3, 0, and we want its region in the first quadrant, so this is the region we're looking at. The distance we want is basically just the x-coordinate of the graph. So all I'm going to do is solve for the x-coordinate of the graph. Y equals 2 minus 2/3 x, like so. Solve for x. Y minus 2 equals negative 2/3 x. Multiply both sides by negative 3/2, and I get negative 3/2 y, plus, what would that be? Negative 3/2 times negative 2 is just positive 3. Equals x. And now that I have this, I can plug this in as my side length. I know because I'm in terms of y, I'm going to be going from 0 to 2, not 0 to 3, because I want y's to be my bounds. So integral from 0 to 2, and I just plug in side, which is negative 3/2 y plus 3 squared dy, like so. And then it's just a matter of squaring this out and solving this. This thing's fully set up. Daikun, I got you. Sorry. That is not Daikun's fault. But it is now locked. All right. And now here we go. And feel bad for these folks, people. Because imagine how sad your life is you get your rocks off by, is that an appropriate term? I'm not sure. By trolling a small educational stream. Anyways, we square this out, and we get integral from 0 to 2. I can pull the 5 onto the outside, and you get 9/4 y minus that. Expansion is a little, I'm going to actually show work here, negative 9/2. Oh gosh. Okay, so I'm going to use the box method because explaining this without losing people seems like close to impossible. And the box adds clarity. Cool, so the reason I got 9/4 y squared is because of this part of the box where you multiply those two terms. Then we get a negative 9/2 y, a negative 9/2 y. Those add to be a negative 9y. And then 3 times 3 is 9. And so I get minus 9y plus 9. Daikun, I already hit that person, so. We'll have to go through all this dude's YouTube stuff, but that's fine. Alrighty, moving forward, I now integrate this, and we get 9/4 times y cubed over 3. And yeah, folks, I know I'm doing all this, but on the homework, you could absolutely just type this into Desmos and have it solve it. And then you just plug in a 2. Stuff works out pretty nicely, and this just yields an answer of 30. I don't even want to lose people here, so I don't want to go too much deeper into this, but and do all the hand math. But I mean, you can really just type it in at this step right here and get the right answer, and that's good to go. So setup is really the critical part of these, and that's what matters. All right. Now we have to talk about some new stuff. So, this one is what I want. Okay, so slight segue before we talk about some new stuff. So, why might you have gotten 20? Not sure. Wasn't something obvious there. Okay, so 3D shapes are really cool. We're starting to graph some really awesome things. These are some really, really awesome things. Just a picture of how cool equations can be when you start going into 3 dimensions. This creates this weird looking, like, I don't even know what to call that thing. Here's another pretty cool function. This thing is like a flower or like a singularity. So that's pretty sweet. And this one looks really innocuous. It kind of looks like a square root graph, but because it goes into 3 dimensions, it actually ends up looking like a kind of serrated row of hearts here. So 3D shapes look really cool. These are the things we're starting to build and define and find the volumes of. with this level of calculus. So I just wanted to show these because I think they're really cool. So what we're doing actually is we're taking something like this rectangle and saying, yo, what happens if I spin this around the x-axis? And so try to picture this. Some people are better at this than other people. I know my wife specifically, like, really, really struggles with this, and she's like a very good at math person. So, like, not everybody can see this stuff, but if you think about what this looks like, if you spun this into 3D, what we're getting is it's going down here and spinning around into 3D, and what this makes is actually, and I have no math skills, but if we looked at this from the side, it'd look like a circle, it'd look like a wheel. Or, sorry, by math skills, I mean I have no drawing skills, so, like, I have no perspective drawing. Yikes. Those of you who are art students are probably grimacing with just that. So this is what it looks like if you spin it into 3D. And for a disc like this, like a very easy disc like this would be a super easy thing for us to find the volume of. All we do to find the volume of this is we'd say, yo, this distance is r, and we just do pi r squared h, where h is the height of our cylinder. All right. So this revolving thing is, unlike our cross sections, always exactly the same equation. That equation that we are doing for disks is always, we're going to integrate across the height. And so if I am going to integrate across the height, what I'm going to integrate is pi r squared. And this is it. This is the equation that gets you through all of the revolution problems, rather, is integrate pi r squared. Now, depending on whether or not we're going in the x or y direction, we do pi r squared in terms of x or pi r squared in terms of y. So the in terms of is very similar to cross sections, but only one equation this week. Only one equation for this lesson. So that's going to bring us to our notes. So I'm going to pull up the notes here, which I now have ready, unlike last time. And yes, folks, people who are talking about Intro to Engineering or the Revolve Tool Inventor, or if you've used any other visualization software in robotics or anything, you've probably seen this sort of revolution tool. This is actually something that's heavily used. One of the easiest things to justify in terms of its application. In almost every machining job, in almost every engineering sort of thing, there's some sort of revolution, especially mechanical engineering. Anyways, so our equation in terms of x, you may notice this looks a little bit different, but this is just pi r squared. The r of x is just saying the radius function is going to be in terms of x, and the dx is also signifying x. The nice part about disk and washer method, the methods we're going to be doing, although washers is going to happen again on Monday, is that if it's rotated over the x-axis, you use x. Just like in cross sections, if it's perpendicular to the x-axis, you use x. So the consistency there is like fantastic and wonderful. And makes it a lot easier to solve. Now, another big idea and important thing to think about when doing these questions is what the radius is. And our radius is always from the line we're revolving around to the curve. So to the outside part of the shape. Now you can see on my screen what the 3D graph looks like, and you can see that radius I drew on there is like this part of the graph here, like from the line we're revolving around up to the curve, and you can see the spun around distance there and all that in the 3D shape. So defining this distance is actually really easy, because this distance in this problem is just the height of the curve, which is the square root of x. Sweet. So if I know that I have this equation, pi integral of r of x squared, and I know radius is the square root of x, then this is a really easy integral. Now, because we're integrating across x, I need to use x as my bounds. So 0 to 4 as my bounds. I can rewrite this as an easier looking integral because the square root of x squared is just x, and all I'm integrating is x dx. So if you thought this was going to be really horrible, it's often not. It can be more horrible as we start revolving around harder things, but when we're just revolving around x, this is generally pretty easy. So when I integrate this, I just get x squared over 2. And you chuck in the 4, and 4 squared over 2 is 8. So this is 8 pi. Cool. That was it. That is about as baby as a disk can get there, but is one of these questions. I don't see any panicked questions in here. Let's try y and see if it's more horrible. Here we go. We got a region formed by y equals 9, y equals x cubed, and x equals 0. So our region is the part I'm going to box here. It's rotated over the y-axis. So this time we're going to be in terms of y. Our radius is drawn in this picture, but it's from the line we're revolving around to the curve. So that distance is not x cubed. X cubed is this distance. X cubed is equal to y, so it's a vertical distance. To find the other one, I'm just going to solve for x in that equation. So y equals x cubed, cubed root both sides, booyah. X found. Sweet. Now, I'm going to be just plugging into my pi r squared equation. My y bounds are 0 and 9. Notice how it would have been a pain in the butt to find this because the cubed root of 9 would have been the x value of this point. I don't know what that is, but I don't need it because I'm doing in the y direction. Feels good. Now, what I'm plugging in as my radius is the cubed root of y. So that's y to the 1/3 squared y. This one is a little more work than the other one because we're going to get a y to the 2/3. We don't just get an easy x piece this time, but besides that, the problem is not more complicated. We integrate, we get y to the 5/3 over 5/3, and then we just chuck in 9, and you get pi times 9 to the 5/3 over 5/3. Chillin'. Cool. That is disks. Now, the reason why there's washers in this is disks are our easy kind, because disks, all we have to do is figure out the distance from the wall here to our curve. The reason why this, the way this can get more tricky is what if you're not revolving around the y-axis? So we're going to head to my scratch pad here, and we're going to revolve over something that isn't the y-axis. And this is where things get a little bit trickier. So, what kind of shape do I want to revolve? Let's revolve something pretty easy. Let's say we got y equals x here. So, okay, I can just solid line this dude. And I cut it with x equals 4. So these meet at 4, 4 up here. This is my region. And I'm revolving this around the line x equals 4. So I'm going to, instead of revolving around x, I'm going to revolve around x equals 4. So this makes things actually easier in this problem also. If I was revolving, okay, if I'm revolving over x equals 4, it's this straight up and down line that I drew here. This straight up and down line, does this look more like the x-axis or the y-axis? And the answer to that is it looks more like the y-axis. So even though it's x equals 4, because x equals 4 is parallel to the y-axis, we're actually going to be doing the question entirely in terms of y. So what that means is I'm going to be using this equation. So pi r of y squared dy, like this. And really it's like that. Okay, so I know x equals y, or y equals x, is the equation of this line. However, because I'm revolving around the line x equals 4, which is here, I actually want to find this distance. So if I use x, or y, rather, because x equals y is our equation in terms of x, I'm actually using the wrong equation, because x equals y gives me this distance from the y-axis to the curve, because it's the x-coordinate of the line. And what I want is actually this other distance. And if this distance is y, then this distance is 4 minus y. So this is where things get more serious here. So again, this distance is y because I solve for it in terms of x equals y, and this distance is 4 minus y, and 4 minus y is actually what I need in order to solve this question. Now the y values I'm integrating across are still my lowest and highest y values, so it's an integral from 0 to 4. My radius in terms of y, I know now it's 4 minus y. And boom, I just solved this equation. I could just plug this into Desmos. Let's see what I get when I plug this into Desmos. So let's do pi times the integral from 0 to 4 of 4 minus y squared dy. Boosh. Answer. Done. Chillin'. Alrighty. How are people doing? Could you also shift y equals x 4 to the left and do a normal y one? Also shift y equals x 4 to the left and do a normal... Yes, you could. So, if you don't understand what Nick just said, this question is exactly the same as if I took y equals x here and I shifted it 4 to the left, so it's no longer y equals x, and it's y equals x minus 4, or x plus 4 rather, because it's shifted 4 to the left. And if you now revolve this around just the y-axis, this would get you the same answer as what I did here, because it still creates this TP problem revolving around that line. And it ends up being exactly the same. So yeah, there's more than one way to do these kinds of questions, and so that's some creative thinking and potentially useful in a lot of problems. This would have gotten you to the exact same spot. And if you check what you get when you solve for y, you notice you get exactly the same thing. Check this out. Look, you get y minus 4, which if you square is exactly the same as 4 minus y. So, ooh. Yeah, and you are integrating from -4 to 0, yeah. So it'd be pi times the integral from -4 to 0 of y minus 4, or y plus 4, or y minus 4, right, squared. like that, and that yields you the exact same answer. So creativity actually pays off in a lot of cases in these sorts of questions. Okay. So let's pop back and see if there's anything I didn't talk about. No, that's all the same stuff. X-axis, Y-axis, revolving around axis with bands, yeah. Could you do a washers with a smaller triangle on the inside? I'm actually not assigning any washers today. I was going to do washers next time, but washers, if you're curious what washers are compared to discs, is in discs, the axis you're revolving around is always a side of your shape. So if I took this piece and revolved it around X or around Y, it would create a bunch of discs. If I spin these into 3D here, it creates a whole bunch of disks. That's why this is disks. If I take something like y equals x and y equals the square root of x, like we had this question earlier, and if I revolve this around the x-axis, what I'm getting is actually something that's this with a gap in the middle. This is still spinning around into 3D like this, but there's a gap inside. And when you have this gap, we actually use the washer method. And the only difference between the disk and the washer method is the washer method, the disk method is always pi r squared. And the washer method is always pi times the big R, the outside function, squared, minus pi times the little r squared. So it's like two washer problem, or two disk problems. So all a washer problem is like two of today's problems. And that's it, difference-wise. The homework is on AP Classroom. We'll see how you guys do. It seems like people are burning out some here. We're starting to lose people precipitously. Seniors, this is our last assignment before I am not checking them anymore. If you want to continue trying them out to like try to learn things, that's fine. This is the last homework assignment for seniors. Is the one today. Are the solids always revolved around the axes? Andrew, if you missed what I did just previously, no. So like this question, I revolved around x equals 4. So in Calc AB, and honestly for a while, you're going to be only going around vertical or horizontal lines, not slant lines, because that makes life way harder. So they'll always be vertical or horizontal, but not necessarily the axes. Oh, yeah. Diagonal line is way harder, like way, way harder, like magnitudes of difficulty higher. So, no, we are not doing diagonals. Alrighty. Well, hey, thanks for showing up. Seniors, good luck with your last assignment here. And make sure you do it so I can change your grades as much as possible. I don't know what I'm going to be doing your grades. There's a fair amount of drama behind the scenes right now because the district's changing things at the last minute, which is fairly normal. But sorry if things seem a little confusing right now from all your teachers. It's going to stay. Do diagonals use the Pythagorean theorem? Yeah, like distance formula? Yeah. But even that, you need to maximize for the shortest distance to the curve. Oh gosh. You're dealing with angles? Oh man. I don't remember how to do diagonals exactly, because they're really hard. So don't worry too much if you're like, I don't know how to do that, because that's really normal if you don't know how to do that. So, yeah. Adios, amigos and amigas. Bye-bye.